Okay, let's look at rectilinear kinematics for continuous motion. We're going to start with straight line motion. Keep things easy, so motion in one direction only. And we need to start by defining a particle. Everything we're looking at so far is going to be something with mass m and negligible size. This means it's not subject to any external forces that would cause it a rotation. We will get into that. Right now, what we're looking at is a point mass. And until, let me think, chapter 16, we will be only looking at point masses, or thinking of the object in the problem as a point mass. We're going to move on to what are called rigid bodies. That is in your future, and that would be something where you have some point A and some point B always connected by some same distance, and imagine this thing translating and rotating at the same time. We're going to learn how to study that motion. First, we need to start with some definitions. Common misinterpretations, can't spell, is position versus displacement. Okay, so position, if we just look at a single dimension, let's look at the x direction. Position is just some number that describes how far away it is from some origin or translating reference frame. This S is interchangeable with X or Y or Z, or R, it can be lots of things. Displacement, on the other hand, is, let's say we have an origin, but our particle starts at some point S and then moves over to some S prime. The position, or the letter S, describes the position from the origin, same as S prime. But if we look at the difference between the two, or delta S, that is what we call displacement. So in order for displacement to occur, some time had to have passed, something had to have happened. One points a finger at where an object is, the other one tells you where something moved from one point to another. And we can say delta S is equal to some S prime minus S then. Okay, if we take this delta S and divide it by the amount of time that's passed, we're going to get our first definition, and that's our average velocity. So what if we take this one step further? Let's take the limit as delta t goes to 0 of delta S delta t, and we're going to get our instantaneous velocity definition, which we will use much more often as a derivative of position with respect to time. Alright, we're going to hold on to that one. It's our equation number 1. I'm going to use it to derive some other equations in a moment. So we have average velocity and average speed also. The only difference is speed would be a scalar, and velocity has a direction with it also. So speed would just be the total distance traveled divided by the time elapsed. So it doesn't matter what direction you're going. And in this case, what if I looked at the average velocity of something that came out to here and came all the way back, that would be equal to this being s and this being s coming out here to some s prime and back here to some s double prime. That gives us an average velocity of 0, but the average speed would be whatever this distance is, s times 2 divided by the time, because it went this distance and then it came back the same distance. So there's a difference in the definitions. Okay, let's look at acceleration now. And note, that's the first derivative of position. If we had position as a function of time, I can find velocity by taking the derivative of position with respect to time. And we'll get more into that. Okay, so acceleration, for our basic average acceleration definition, we just need to know 2 points where we know the velocity and the time that is elapsed. So whatever our change in velocity is and whatever our delta t is in that case. So we can say whatever our final velocity is minus our initial velocity over delta t. Once again, we can take the limit as delta t approaches 0 of delta v delta t, and we get our definition dv dt, which is our acceleration, the derivative of velocity with respect to time. We can also say this is the second derivative of position with respect to time. Okay, so if right now I have that velocity is equal to ds dt, and acceleration is equal to dv dt. Those are our new definitions. One tool that we're going to use is to eliminate dt from these, and I'll show you why. If we eliminate dt, taking this one, that would make ds equal to b dt, or dt equal to ds over v. If I take this one, it would be dv is equal to a dt, or dv over a is equal to dt. Now I'm going to set them both equal to each other because they're both equal to dt. I get ds over v is equal to dv over a. Do cross multiplying or solve this or simplify this however you've learned, and you will find we get v dv is equal to a ds. We will use this equation and integrate it to find out what the velocity is if we know the acceleration and things like that. Just hold on to this for a moment. We'll get there and get to its uses, I promise. First, let's look at constant acceleration. So this is it's just equal to a number, right? Some number meters per second squared. Excuse me. And this can often be a constant like gravity, which is 9.81 meters per second squared. We are going to derive velocity as a function of time for constant acceleration. You've seen these equations before, but you might not know where they came from. So let's start with our definition that acceleration is equal to dv dt. And by the way, you have to be able to do this. You have to be able to integrate this equation. You have to be able to integrate these equations to get your constant acceleration equations, and it goes one step further for when the acceleration is a function of time, and we'll get there. Right now, let's look at constant acceleration, so we can put a C right there. The definition of acceleration is the derivative of velocity with respect to time. Let's rearrange this by separating variables and say dv is equal to the acceleration times dt. I'm going to integrate this from some v naught to some v final, and this from some 0 to some t. You could do some t naught to some t final also. We're just going to get the constant pulled out times the integral from 0 to t dt. And when I integrate dv, I'll get v final minus v naught. And when I integrate dt, I'll get a t, and then multiplied by the constant acceleration. So we have the final velocity is equal to its initial velocity plus the constant acceleration times time. Y'all have seen that since maybe 7th, 8th grade even. Okay, let's do position as a function of time. Alright, we're going to start out with velocity is equal to ds dt. And I'm going to separate variables to say ds is equal to v dt. A lot of students will often hang up on a test not knowing what to do at this moment. We have an equation for v. Let's put it in there. So we'll say v naught plus acceleration times time dt, and that's all equal to ds. Now I can integrate from some s naught to some s final, and from some 0 to some t, and we get s final minus s naught is equal to v naught times time plus 1/2 acceleration times time squared. Move this on the other side, and you have seen this equation before. Might not have found or known where it came from though. So these only work for constant accelerations. Keep that in mind. Let's do one more. Let's do velocity as a function of position. This is your v squared one. Okay, so in this one I need to either go to that a ds is equal to v dv, or start back at the acceleration is equal to dv dt, solve it for dt, and v is equal to ds dt, solve it for dt, and set them equal. But it's perfectly fine to start from right here. I am going to integrate from some s naught to some s final, and in this one some v naught to some v final. This will give me a v squared. We're going to evaluate that, v squared over 2. We evaluate that from v final to v naught, and we'll get our constant acceleration pulled out times some s evaluated from s final to s naught, and rearranging, we get v final squared is equal to v naught squared plus 2 times that constant acceleration times s final minus s naught. This is often delta s or delta x. There we go. We have 3 kinematic equations, but they only work for constant accel. Don't forget that.